Hi everyone, my name is Mudawat Lakshman from third semester CSA F section. So today I am going to explain about cache memory from the subject Computer System Architecture. So now we'll move to the introduction part of cache memory. Introduction to cache memory. Cache memory is a small high-speed storage layer located close to the CPU. It temporarily stores frequently accessed data and instructions to reduce access time. Cache improves overall system performance by minimizing the latency of data retrieval. So here, cache memory is a small but extremely fast type of memory that acts as an intermediate storage layer between the CPU and the main memory, that's called RAM. Its primary role is to store frequently accessed instructions and data so that the CPU does not have to wait for their slower main memory. And since the speed of processors has increased much faster than the RAM, this gap causes delays in a data retrieval. Cache memory helps bridge this gap by offering faster access, thereby reducing latency and improving overall system performance. Essentially, whenever the CPU needs data, it first checks the cache. If the data is present, the CPU saves times, and this makes cache an essential element in modern computer system. So we got the cache memory. It's like it has a it's an intermediate storage layer between the CPU and the main memory. So this is the introduction part of cache memory. And next we'll move to the importance of cache memory. So what is cache memory and all? What is the importance of cache memory? So cache memory is a small high-speed. Yeah, we're done with the introduction part. Next importance of cache memory. So cache reduces the average time required to access data from the main memory, and it helps in bridging the speed gap between the CPU and RAM. Effective cache management enhances the efficiency of processing tasks. So here the important the importance of cache memory lies in its ability to reduce the average time required to access data from memory, because the CPU is much faster than RAM. Without a cache, the CPU would spend a significant amount of time idle by waiting for data. Okay, cache acts as a high speed buffer that ensures instructions and data are delivered quickly to the CPU, allowing programs to run faster and more efficiently. By storing commonly used data, cache memory minimizes repetitive retrievals from slower memory, effectively improving systems throughput. In short, cache we can say that cache is a key component that balances the performance gap between the CPU and the RAM, making the system more responsive. And next we'll move to the slide of types of cache memory. How many types of cache memory are there? We'll discuss here. Uh, Types of cache memory. So cache memory are like, there are typical three levels like L1, L2 and L3 cache, each with the different sizes and speeds. L1 cache is the smallest and fastest, located directly in the CPU core, and L2 and L3 cache are larger but relatively slower, often shared among multiple cores, and relatively these are slower than L1, we can say. So cache memory is typically organized into three levels. Those are L1, L2 and we can say L3. The L1 cache is smallest and fastest, located directly onto the CPU core. So the L1 is directly located on the CPU core and it stores the most frequently used instructions and data. The L2 cache is larger but slightly slower, and depending on the process design, it may be dedicated to a single core or shared among multiple cores. The L3 cache, among this L1 and L2, the L3 cache is the largest but slower compared to L1 and L2, and it is usually shared by all cores in multi-core processor. This multi-level approach allows the system to strike a balance between speed and capacity, ensuring efficient use of memory resources. And we'll go with, we missed the slide here. Key features. What are the key features of cache memory? Faster than RAM but smaller in size. Acts as a buffer between CPU and RAM. Uses SRAM, that means static RAM instead of DRAM used in main memory. We know the DRAM, dynamic RAM, we use in RAMs like normal RAMs. We use static RAM in these cache memory. Reduces CPU idle time by providing quick data access. And we'll go with cache organization and structure. So what is how the cache is organized in the processor and what is the structure of the cache? We'll discuss here. Cache memory is organized into blocks or lines which contain data and metadata like tags. The organization can be directly mapped fully associative or set associative. Each organization impacts the cache hit rate and complexity of management. Here, cache memory is organized into blocks, often called cache lines. We can call them cache lines also, each containing a piece of data along with metadata such as tags. There are different methods for mapping data from main memory into cache: direct mapped, fully associative, and set associative, and all these. In direct mapped cache, each memory block has one possible cache location, which is simple but prone to conflicts. Fully associative cache allows any memory block to store in a cache line, giving flexibility but increasing complexity. And last, set associative. Set associative cache strike a balance by grouping cache lines into sets, where each block can map to any line within a set. The organization directly influences the hit rate overall the cache efficiency. And we'll go with the what is cache hit and miss. This terminology, what are the terminologies we use in hit and miss, what they are belong to and all. A cache hit occurs when the requested data is found in the cache, reducing access time, and a cache miss happens when the data is not in the cache, leading to fetching from slower memory. Strategies like prefecting and replacement policies help mitigate cache misses here. So when CPU requests data, well, suppose when CPU requests data and it is found in the cache, this is called cache hit, okay, and it results in the faster data access. On the other hand, when the requested data is not present in the cache, and here it is a cache miss, and the CPU must fetch the data from slower main memory, causing delays. To improve the chances of cache hits, techniques such as prefecting. Prefecting means loading data before it's actually needed, so that's prefecting, and efficiently replacement policies are used. The effectiveness of cache is often measured by its hit ratio, which represents how frequently cache provides the needed data. Next, we'll go to the cache replacement policies. What are the cache replacement policies? Replacement policies determine which cache line to replace on a miss. Common policies include like least frequently used (LRU), first in first out (FIFO), and random we use in stack data structures and all. The choice of policy effect and the efficiency of cache utilization and performance. So when a cache miss occurs, the system must decide which existing cache line to replace with the new data, and this is handled by replacement policies like LRU and FIFO. So LRU, the data that hasn't been used for the longest time, which generally works well in practices, and in FIFO policy replaces the oldest data in cache regardless of its usage pattern. Okay. Another method is random replacement policy. In the random replacement policy, which replaces a randomly selected block, the choice of replacement policy greatly affects the cache performance because it's influence how effectively cache space is utilized. And we'll go with now cache coherence and consistency. And here, cache coherence ensures consistency of data across multiple caches in multiprocessor system. Protocols like MESI MESI means modified, exclusive, shared, and invalid. MESI manages the states of cache lines to maintain data integrity. Maintaining coherence is vital for correct execution and system stability. So in multi-core systems, each core often has its own cache, which can lead to problem of inconsistent data. If one core update a value while others still use an old copy, this issue is solved through cache coherence protocols like MESI, just we discussed it, modified, exclusive, shared, and invalid, which ensures that all cache maintains a consistent view of memory. Maintaining cache coherence is crucial for correctness in multiprocessor systems, as failure to do so could cause incorrect program results. Although coherence mechanisms add overhead, they are essential for stability and readability of modern computer architectures. And what are we go to the next slide. Advantages of cache memory. What are the advantages? So cache significantly speeds up data access compared to main memory. It reduces bottleneck caused by slower memory systems. Cache also helps in energy efficiency by reducing the number of memory accesses. So the biggest advantage of cache memory is speed, because it's on the core of the processor. So the biggest advantage of cache memory is the speed only. It provides significantly faster access to data compared to main memory, which means the CPU spends less time waiting and more time executing instructions only. So this not only improves performance but also reduces the bottleneck caused by the RAM. Okay. So it means the cache is much faster than the RAM, so it can reduce the bottleneck caused by the slower RAM. Additionally, cache memory contributes to energy efficiency. Since accessing cache assumes less power than accessing main memory, overall cache memory enhances both speed and efficiency in computer system, making it indispensable in a modern architecture. And next we'll go with if there is advantages, there will be the limitations and challenges in everything, in every concept. So we'll go for the limitations and challenges of the cache memory. Cache size is limited by physical and cost constraints, impacting capacity. Cache misses can still occur, especially with poor locality of reference. Managing cache coherence in multi-core systems add complexity and overhead. Here, despite its advantages, cache memory has certain limitations. First, its size is limited due to the cost and physical constraints, which mean it cannot hold all the data the CPU might need. Second, the cache misses still occur, especially if a program does not exhibit good locality of reference. In multi-core processors, ensuring cache coherence, introducing complexity and additional overhead in communication between cores. Thus, while cache improves performance, managing it effectively remains a major challenge for computer architecture. And next, we'll go with the conclusion now. The last slide. Maybe. Sorry, the conclusion. So, we'll go with the conclusion now of the cache memory. So we can say that in summary, cache memory plays a vital role in computer system architecture by reducing the speed gap between CPU and RAM, thus enabling faster data access and the better system performance. And its hierarchical structure, efficient organization, and replacement policies, it a powerful tool for speeding up execution. However, challenges like limited size, cache misses, and coherence issues in multi-core systems remain areas of active research and optimization. References such as Tenenbaum's modern operating system, Hennessy and Patterson's computer architecture, and Stangling's computer organization provides an depth insight into design and functioning of cache memory in computer system. So this is all about the cache memory in a computer architecture and system. So we have it's like the cache memory is references such as Tenenbaum's modern operating system, Hennessy and Patterson's computer architecture, and Stangling's computer organization provides an depth insight into design and functioning of cache memory in computer system. So this is all about the cache memory in a computer architecture and system. So we have it's like the cache memory is very much. This is all about the cache memory.